All right, so let's continue looking at section 6.1. So we talked about angles and how we measure them. We're going to talk a little bit more today about a couple things. We're going to talk about arc length, and we're going to talk about another concept called angular velocity. Yep. And then, depending on where we stop, the last topic for the week is unit circle trig. That's section 6.2. All right, so we'll definitely get through arc length and angular velocity, and then you can let me know if you want to start unit circle today. All right, so first thing, I'm going to show you about arc length. I'm going to draw a picture, and I think it'll help what I'm about to write make more sense. Here's a circle, okay? I'm going to draw an angle inside the circle, right there. There's my angle, and the arc that is created from that angle is in blue, right there. Okay. How big of an angle did I draw in red?
90.
I drew a 90. Okay. So let's do it again. Here's a circle. This time, I'm going to draw my initial side, my terminal side, and my arc in blue. How big of an angle did I do this time? 180. If you compare the size of the angle the first time, it was 90, to the size of the angle the second time, it was 180. What happened to the size of the angle?
Doubled.
It doubled. Now, look at the length of the arc in blue. How much of the circle does it take up on the 90? A quarter of the circle. Look at the length of the arc in blue for the one on the right. How much of the circle does it take up there? Half. It doubled. So what I'm showing you here is if you double the size of your angle, you double the size of the arc. If you tripled the size of the angle that you started with, you would triple the size of the arc. And it works the other way too. If you made the angle half as big, the arc would come out half as big. What that means is they are directly proportional. As one changes, the other one changes by exactly the same amount. And if you look at the first part of the word proportional, you have proportion. So what we're going to be able to do is set up a proportion to figure out the formula for arc length. Right? We're only going to have to set the proportion up one time. The proportion is just to figure out the formula. Once we know the formula, then all we want to do is memorize the formula. All right, so what I've drawn here, kind of like the other diagram, except I've put two angles in the same circle. I've labeled each angle using theta. One of them is theta, one of them is theta 1. And then the arcs that are created from those angles are S, created from angle theta, and S1, created from angle theta 1. And R is just there to mark the radius. I didn't label all four of those as R, but they're all R. It's the radius. Okay, any questions on that picture? So now I think we mentioned this yesterday, but I'm going to talk about like feet and inches. Again, because I think it's a simple one to kind of relate to. If I wanted to create a proportion to convert between feet and inches, I have to fill in something I already know, right? You got to have a fact that you already know between feet and inches. And I think, Jake, you mentioned it yesterday. What was the connection between feet and inches? 1 foot is 12 inches. How did you know that? Yeah, we talked about this yesterday. So it's just a fact that we already know. At some point we learned it's true, and we're using it. Now, because Jake picked a 1 and a 12, does that limit what numbers I could plug in here? Like if somebody said 80 inches, could I convert 80 inches to feet? How about 23.2 inches? 99.6? Anything, yeah. He picked a 1 and a 12 on the left, but I could plug in, you know, anything there. And then I could solve for the other thing. We just had to start with something we already know was true. Okay, the connection between feet and inches. Well, we got to do the same thing here. We have to start with something that's already true. And what we're going to do is we're going to pretend that one of these angles is a certain size. And if we do that, then something special will happen. This arc that I drew in red and the radius, they come out exactly the same length if this angle is a certain size. Does anyone remember from yesterday? It was before we even converted between degrees and radians. It was a picture. And I said if this angle is a certain size, and I told you, then the length of this arc is the same as the length of that radius. Remember? Again, that angle has to be a certain size, and if it is, the length of the arc in red and the radius are the same number. But it only happens if that angle is a certain size. And that's what I need to know. What was your guess, Jane?
45.
45? No, it's not a 45. It's measured in radians. Yeah?
1 radian.
1 radian. Yeah. So we said yesterday that if you draw an angle of 1 radian and you measure the size of the arc and you measure the radius, they come out exactly the same. I think it's the very first thing under degrees and radians yesterday. So that's going to be our starting point. That's like our, all right, 1 foot, 12 inches. 1 radian, then that makes the arc length equal to r. Okay? It's just like background knowledge. Jake explained it. Right. So what we're going to do is we're going to set up a proportion, and then we're going to fill in the fact that we know is true. So let's set up a proportion. Now, there's lots of ways you can set it up as long as you're consistent. If you do feet in the top on the left, you got to do feet in the top on the right. Well, I'm dealing with an angle and an arc. So I'm going to set it up as angle over arc. So I use those two. And on the other side, I'm going to set it up as angle over arc. What's my other angle and my other arc? About Connor?
Would be theta.
Theta, it's my other angle. And my other arc?
S.
S. And the reason I can do that is because those 4 things are directly proportional. That's the first thing I showed you. This angle compared to this arc is proportional to that angle compared to that arc. Now we're going to fill in our 1 foot, 12 inch fact. That's not our fact, but it's the starting fact. Right? So we're going to let theta 1 be 1 radian. And that would automatically make S1 equal to R. So anytime you make an angle of 1 radian, you've automatically made the arc the same size as the radius. Why? Same reason why there's 1 foot and 12 inches. It's the way it works. And now the other side, you leave blank. That's the side you don't fill in anything for. Leave it the way it was. And now we're going to solve it. How do you solve a proportion? What do? You cross multiply. So we have 1 times S, which is just S, equals R times theta. And that's the formula to find the length of an arc. S equals R theta. So S is your arc length. R is the radius of your circle you're dealing with. And theta is your angle. But the angle has to be in radians. Why does it have to be in radians? Because way back when we started the whole thing, we assumed that our angle was in radians. So it's just like if somebody gave you this formula, 1 foot equals 12 inches, and they wanted you to convert between feet and inches, well, you've got to use feet and inches. You can't plug in like centimeters into this. That's not the units you started with. You started with feet and inches, so you're going to end with feet or inches. Depends which one you're solving for. We started with radians. We're going to end up with radians. Okay, so there's 3 things in the formula, and the way it works is they always give you 2 out of 3 of the things. You fill in 2 and solve for the one you're missing. Okay. Any questions on the arc length formula? So we're going to use what's in that box on the next few problems. So sometimes when they give you a problem, they'll just write it out. Sometimes they'll draw a picture of it. Sometimes they'll do both. So in this one, I did both. So I want you to find the length of an arc. I drew it in red. Of a circle. The circle has a radius of 2 inches. And the angle is pi over 4. And there's no degree mark, so we know it has to be what unit? It's in radians. Yep. All right. So the question is asking about an arc. It gives me a radius and it gives me an angle. So there's the 3 things we just talked about. Angle, arc, radius. All right. What's my arc length formula? We'll start with that.
S equals R theta.
Yep, S equals R theta. Let's just make sure which one, we know which one they're asking me to solve for. What's the one letter that I don't know in this problem?
S.
Yep, find the length of the arc. So S is the one we don't know. So that means we must know the radius. Michael, what's the radius?
2.
2. And we also must know my angle. The angle is pi over 4. Okay. So now we just multiply. If you want to think of the 2 as a fraction, you can put it over 1. Just multiply straight across. 2 pi over 4. And what is 2 pi over 4 reduced to?
Pi over 2.
Yep, pi over 2. And now, I want to remember what we just found. We just found S. Someone remind me, what's S again? It's the arc length. It's a length. So you've got to put a label on it. To figure out the label, just go back and look at the problem. What units did they use to represent length in this problem? Inches. So that's pi over 2 inches. Or if they wanted it as a decimal, it's about 1.57 inches. And that's it. That's how you use the formula to find the arc length if you're given the radius and the angle. Questions on that one? No reason to write it as a decimal unless they ask you to. If they don't, I would leave it just like pi over 2. All right, let's try this one. This time there's no picture. You don't really need a picture. And it's a little different. It says find the radius. So this time you're finding the radius. They're not giving you the radius. The arc length is 3 pi feet. And the central angle is 60 degrees. Kylie, can you remind me again, what's the formula we used in the last problem?
S equals R the circle with the line.
The circle with the line in the middle. Anyone reminder, what is that called? Theta. Yep. Theta. Theta. All right, and we're finding the radius, so we don't know that. So let's start with S. Shai, what's S in this case?
S would be 3 pi.
Yep. So the arc length is 3 pi. R, I don't know. Times. And what am I going to put into parentheses right here?
Not 60 because it's not radian.
Right, I'm not putting 60 because that's a degree. If you put 60, it comes out wrong. What do you have to do with 60? Yep. That one's pi over 3. Yep. If you're not sure, you just convert it. 60 goes into 180 3 times. So leave it as pi over 3. Okay. Now I want to get r by itself. So I want to move the pi and the 3 to the other side at the same time. It's kind of like if you had this, and you wanted to move the 3 and the 4 to the other side at the same time. Does anyone know what you do to move both at the same time?
Multiply by the reciprocal.
Yep, you multiply by the reciprocal. Michael, what's the reciprocal of pi over 3?
3 over pi.
3 over pi. 3 over pi. Pi's cancel, 3's cancel, r is by itself on the right. Emily, what cancels on the left? The pi's. And I'm just left with 3 times 3, which is 9. And what does r stand for? Radius. Is the radius a length or is it an angle? It's a length. It's a distance from the center of the circle to the edge. So what units on this one? Feet. This one would be in feet. You always get your length unit from whatever the length unit is they used. And that's how you'd solve for r. Okay. The only other type we didn't do is solving for, bless you, solving for theta. Okay. I didn't have one solving for theta, but does anyone want to see one solving for theta? Sure. Okay. So we'll just make it example 6c.
I have a quick question. If you were to multiply 60 by pi and then divide by 180, would it still work?
If you wrote it as a decimal, yeah, what would happen is you'd probably get like 8.999 feet.
Oh.
It would be a little off because it would be rounded. Or 9.0001 or something. Yeah, that would be close. But yeah, if they don't ask you to round it, don't worry about it. All right, so let's see. So find theta. I'm just going to really simplify it. If r equals 4 centimeters and s equals 5 pi centimeters. So find the angle if the radius is 4 and the arc length is 5 pi. So find the angle. I'm even going to throw in one extra step here. Find the angle in degrees. When I use this formula, it's going to give me an answer for the angle. But what unit is the angle going to be in from this formula? It's going to be in radians. So let's go through and we'll get the answer first in radians and then we'll change it. So the arc length is 5 pi. The radius is 4. And the angle I don't know. So now there's just one step. Rebecca, how would I get theta by itself?
Divide by 4 on both sides.
Divide by 4. Divide by 4. And the angle is 5 pi over 4. And what's the unit on it again? Well,
radians, sorry.
theta represents what? It's an angle. Are angles measured in centimeters? No, angles are measured in
Radians or degrees.
radians or degrees. What's this one?
Radians.
It's radians because that's what the formula gives. So do I have to put RAD after it?
No.
No. So that's the angle, but that's in radians. Let's change it to degrees. Let's see if we can use the shortcut. Does anyone remember what pi over 4 is? That's a 45 times 5. So 45 times 5 is 225. So there's your answer, and that one's in degrees. So that little extra step at the end, changing to degrees, that was just more of a annoying step. They might not ask you to do that normally, but if they do, that's how you do it. Okay, so that's every variation you could have on that problem, finding all three things. Questions on the formula? Okay, so the last thing in this part is angular velocity. So I'm going to explain a little bit about what that is. And then we're going to be doing some conversions. So angular velocity, the default unit is radians. I'll say this again, but when they ask you to find angular velocity, always use radians. There are other things you can use, but if they don't tell you, use radians. And angular velocity is used to measure the speed of something spinning. Okay. Bless you. All kinds of things are measured in a spinning speed. If you think about your car, it usually has a speedometer. That's just how fast your car is going, like in a straight line. But it also, a lot of cars have a tachometer. Usually it's numbered from like 1 to 8 or 1 to 9, and that's how fast the engine is turning in RPMs, how many revolutions it's making per minute. So that's an example of angular velocity, RPMs. What else? Certain power tools, like you might have a drill, and it might say the drill spins at 1,000 RPM. There are some really high-speed tools, like a Dremel. Anyone ever heard of that? Dremel, it's like a really, really high-speed tool. You can use it for like cutting and engraving, all kinds of things. That might spin at 30,000 RPM. And maybe you can control the speed. Different metals might have different hardness, so if you're engraving, you might need a faster speed for a harder metal or a slower speed or whatever. But different things are measured in spinning speed. So why do we need that? We already have a way to measure speed, like miles per hour. And that measures the speed of something going straight. So why do we need something different when it's spinning in a circle? Well, I'm going to try to show you. I've got a disc here, and there's 3 dots on it. Okay. I should probably make them all different colors. You have a black, a red, bless you, and a blue dot. All right. And they're all grouped together. So what I'm going to do is I'm going to spin that disc one time. Okay, I'm going to make one full revolution, putting the green handle back at the top. So they all just made one revolution. Does everyone agree on that? Okay. Which dot traveled the farthest? The blue, right? It was on the outside edge, and it went the farthest. Does everyone agree on that? Okay. So here's your formula when you're dealing with linear speed. Distance equals rate times time. So we all agree that the blue dot traveled the furthest, the red dot was like the second furthest, and the black dot, basically it just stayed still. Stayed right in the center. All right. Now, if I do it again, this time I don't want to focus on how far they're going, I want to focus on how long it takes each dot to make one revolution. So if you just watch them, going around, then I'm stopping. They all just made one revolution. If you compare the time it took the black dot to make a revolution, the red dot, and the blue dot, how do the times compare? So they're all the same. They all made one revolution in the same amount of time. But the blue dot went further than any of the other ones. So what does that mean? if the blue dot went further in the same amount of time, what does that mean about its speed? Think about like you leave your house, your friend leaves your house, you both leave and drive for an hour. Your friend ends up further away than you do, assuming you're on the same road. And there's no traffic lights, and there's no other traffic, just you and your friend on the only road. That's it. So what does that mean? Yeah.
One is going faster than the other.
Yeah, it means that the blue dot is going faster than the red dot. So that's kind of confusing, because they're all on the same disk. The further out you get from the center, the faster the dot is moving if you think of it as a linear speed. That's the problem with linear speed. Every single point on the surface of the disk, from the center to the edge, is traveling at a different speed. Very confusing. If you think of it as angular speed, they're all going the same speed. They all made one revolution, and maybe it took me 3 seconds to bring them around. So it's just a way of describing the speed of this disk using a single number for every single spot on the disk. That's what angular velocity is used for, describing the speed of something spinning. Right? So that's why we use it. So again, I already said it, but angular speed is measured in radians per whatever. There's no standard on the time unit. It can be minutes, seconds, hours, days. Minutes is a common one, like when you talk about RPMs. Okay, there are a couple units you might see abbreviated a little differently because they're used a lot. When you write revolutions per minute, you can write revolutions, fraction line, minute, or you can write the 3-letter abbreviation, RPM. Same thing with miles per hour. Miles per hour can be written as miles, fraction line, hour, or the 3-letter abbreviation, MPH. Those are the only two that really use 3-letter abbreviations. Everything else, you just write it as a fraction. So that's angular speed. Comparing that to linear speed, that's the speed of an object just going in a straight line. Okay, that's what, if you get pulled over, that's what you're going to get pulled over for, linear speed. 60 and a 40. You're not going to get pulled over for your RPM speed. You're going 2,000 revolutions per minute. You don't get pulled over for that. That's the speed of your engine, not the speed of your car moving. Okay, and that can be measured in a lot of different units. Miles per hour, probably the most common one that we can kind of visualize. Feet per second. If you're in pretty much any country besides the US, it's going to be kilometers per hour. And a lot of cars have both. If you look at your speedometer, usually on like a US car, the kilometers are the small ones and the miles per hour are the big ones. In other countries, a lot of cars have both too, but the kilometers are the big ones and miles is the small one. And if you've ever used your US GPS in a different country, it's really weird. Has anyone ever done that? Well, if you keep it on like miles per hour and you use it in a country that uses kilometers per hour, all the numbers are weird. Like their numbers seem normal, like 40 kilometers an hour, 50 kilometers an hour. But if you keep it in US units in another country, it'll tell you the speed limit is like 27 miles per hour.
Yeah.
So it's really weird because it's you're in the wrong unit for that country. Or like 47 miles per hour. They don't line up nice. So yeah, if you're in another country and they say the speed limit's 80 and they use kilometers per hour, you better not go 80 miles an hour. That's a pretty huge difference.
Alright.
Yeah. And claiming that you're an ignorant American and you don't understand the difference, it's not going to work.
Are you speaking from experience?
No, I've never actually had that happen, knock on wood, but it's pretty clear. Usually, unless you take your own car to another country, if you rent a car in another country, the speedometer is usually pretty clearly in kilometers per hour. But again, if you take your own car, you just have to be careful. But a lot of cars, even if it's digital, like a digital display, you can probably program it so it's like metric or standard. Same with the temperature. Fahrenheit, Celsius stuff. All right, so the way we're going to convert is instead of trying to learn like formulas and memorizing, we're just going to use what's called dimensional analysis, which is how I've had you convert between radians and degrees. If you want 2 units to cancel, you just put one in the top, one in the bottom, and that's it. Any questions on that? No? Let's convert 3 days to minutes. So in this case, this isn't even a rate. A rate would have distance per time, like 3 days per year or something like that. It's just 3 days. So some basic conversions I'm going to assume that you know, like how many seconds in a minute, minutes in an hour, hours in a day, days in a year. Okay, so you need to know those. For length, you need to know how many inches in a foot, how many feet in a yard, and how many feet in a mile. That's usually the one some people don't remember. As far as any other conversions, like if you ever had to convert between centimeters and inches, that's a weird one. Okay, it's like 2.54 centimeters to an inch. I would tell you that on a test. Okay? But the basic ones I just said you would need to know. All right. When you convert from days to minutes, we're just going to go 1 unit at a time. What's the next time unit smaller than a day?
Hour.
An hour. Right? Even if we don't know how many hours in a day, which we should, we can figure out where days should go. We're trying to cancel it out. It's in the top. Where is it going to go in this other fraction? It's going to go in the bottom. So days or day, depends on your conversion you write. Day in the top, days in the bottom, hours is in the top. And what's the conversion? Hours to days.
1 day, 24 hours.
1 goes in the bottom, 24 goes in the top. So it was either going to be a 24 over a 1 or a 1 over 24. It was going to be one of those two. We want days to cancel. Now if we multiplied it out, we would have hours. What's the next unit down from an hour? Minute. So we have to figure out where hours and minutes go. Should we put hours in the top or the bottom? Bottom. Hours in the bottom, minutes in the top. And what's the conversion between hours and minutes? 60 minutes to 1 hour. Hours cancels, and now you have a time in minutes if you multiply it out. So just multiply straight across. 3, 24, 60, 4,320 minutes. Okay, questions on that? So that's just converting a single number. Let's try a rate. So 50 feet. What does 50 feet per second mean? Like if you had to explain like how far you go in a second, what does that mean to someone? Like if they don't understand 50 feet per second.
Means you're going 50 feet in 1 second.
In 1 second. In 1 second, you go 50 feet. So we'll just break it down like that. 50 feet, 1 second. Now, this is like we're doing 2 problems at the same time. We have a time unit. We have to get seconds to hours. And a distance. We have to get feet to miles. Let's start with the time unit. Seconds to hours. What's the next unit up from a second? Minute. When we're dealing with minutes and seconds, where would we put seconds? In the top. We want it to disappear. Minutes in the bottom. The connection, we already did this, 60 seconds in a minute. So if I stop now, I'd have a speed in feet per minute. Okay. Next unit up from a minute is an hour. Right? So now we're dealing with minutes and hours. Where would minutes go? It goes on the top. Hours goes on the bottom. 60 minutes to an hour. Minutes, minutes. Now you have feet per hour. Okay, so the time is good. We got hours. We got to get rid of feet. So even if we don't know how many feet in a mile, we should know where feet is going to go. Top or bottom? I heard both. Bottom, yeah. So bottom, because you want it to cancel, it's already in the top. Put it in the bottom. Miles goes in the top. So now I need to know in 1 mile, there are how many feet? Yep.
5,280.
Yep, 5,280. Feet in the top, feet in the bottom. Let's check our units that are left. In the top, it's miles. In the bottom, it's hours. So just multiply everything in the top. 60 times 60 is 3,600. Times, what's that, 50? And then you're going to divide by 111. So you really only need to divide by 5,280. So that's a speed of 34.1 miles per hour. So that's an example of converting linear speed to linear speed. All you did was change the units, but it's still linear to linear. Let's try angular to angular. So I'm giving you an angular speed, 200 radians a second, and I want you to convert that to RPMs, revolutions per minute. So this is angular speed to angular speed. So what does that mean? 200 radians per second. If you had to like break that down, like we wrote down 50 feet per second, what does it mean? 200 radians per second.
200 radians in 1 second.
Right, this object is spinning 200 radians, however many that is, in a second. So the key is 200 radians in 1 second. Now, technically, I don't need to put RAD, but it's kind of helpful when you're doing this so you can see it. All right, I'm not going to go through the time unit as slowly this time. How would you convert seconds to minutes? Yep.
60 seconds over 1 minute.
Yep, 60 seconds over 1 minute. That's done. Now we need to convert radians to revolutions. Even if you don't know the numbers, you should know where the units go. Radians on the bottom. Radians, revs. Now, we know how many degrees in a revolution, right? How much is that? 360. I just want to know what that is in radians. So how many 360 is equal to what in radians? 2 pi. So 1 revolution is 2 pi radians. And that's it. It's all set up. Now you just do it all out. So 200 times 60 is 1,200. 1,200 divided by 2 pi.
18,849.6.
Well, it's 1,200, and we're going to divide, so it's going to get smaller. You probably just hit the wrong button. Maybe you hit times.
Hit 200 times 60 divided by 2 pi.
So I divide by 2, I get that. And then divide that by 3.14, and I get 190.
I got the same thing Jake got.
Then I did it wrong.
Well, I didn't divide separately. I just did 2 times pi in the division.
All right, let me type it in the way.
He didn't put any parentheses in.
Oh, yeah, you need parentheses.
Yeah.
Times 60. Do it first like that. Oh, I also said 200 times 60 was 1,200. I meant 12,000. So I screwed that up. And then divided by 2 pi. Let's do it with parentheses, and I'll show you the difference. So that's how you did it, I was right? Okay. Now try it like this. Divided by 2 pi, and watch what happens. So you just forgot parentheses. You did it right.
Mhm.
I think I messed it up. So 1,909.86. Okay, so be careful when you type it in, but I just knew right away. I knew it had to be off because when you divide by 6, which is roughly what 2 pi is, it's about 6, I knew it had to get smaller. And it seems like your answer got bigger.
Right.
So I knew right away something was weird. So 1,009.86. That's revolutions per minute. Okay. Any questions on that? All right. So we started off with a basic one, just converting a single unit. That's a linear speed to a linear speed. That's an angular speed to an angular speed. Now, what we're going to do now is convert from angular to linear, right? And the way you could kind of visualize something from angular to linear is pretend you had that disk again, right? And those 3 dots are glued on the disk. Maybe they're like weights. Imagine all of a sudden the glue let go on one of them. So if that disk is spinning really fast, and whatever was glued on the disk let go, it would go flying off the disk. It would go flying off in a straight line. Same thing would happen with like a lasso, right? Imagine like one of the bull riders, whatever they swing the lasso, and then they let it go. When they let it go, it goes straight towards whatever they're trying to rope or whatever they're doing, all right? So that's an example of something spinning with RPMs. They let it go, and all of a sudden it takes off straight, maybe at 10 miles or 15. I don't know how fast it goes. Right? But that's basically going instantly from angular to linear speed. So let's try it. I'm not going to worry about part A. Part A is doing what we've already done. Convert revolutions per minute to radians per second. We basically just did that. We went from radians per second to revolutions per minute. So that's just the reverse. But part B is the part that's different. Find the linear speed of a point on the circumference of our wheel. Now, I had to say on the circumference because remember, every single point on the wheel is a different linear speed. I want to know the point right on the edge. If the first 2 visualizations don't make sense, I hope they do, but a third way you can visualize it is you imagine you had a tire spinning on a machine, right? 1850 RPMs. And all of a sudden the tire fell off the machine and it hit the ground. It's spinning. If it didn't lose any traction, which it's going to a little bit, but if it didn't lose any traction and it hit the ground, all of a sudden the tire would just take off straight, right? We're trying to figure out how fast would the tire go if it hit the ground and just took off. That's what we're figuring out. All right. So anytime you want to go between angular and linear, you always want to be in revolutions. Doesn't matter if it's minutes or seconds, we can deal with that after. But that's perfect setup. So it's already in revolutions. So it's 1,850 revolutions in a minute. Okay, I'm going to deal with the time unit quickly. In 1 minute, 60 seconds. Okay, so now I have revolutions per second. So my time is good. Now I want to get revolutions to feet. What haven't I used in this problem yet that they gave me? I haven't used the size of the wheel. That's important. Now, they want feet. They gave me 18 inches. Can anyone tell me what 18 inches is in feet?
1.5.
It's 1.5 feet. So 18 inches is 1.5 feet. So they were a little tricky because they gave me the radius in inches, but then they want the final answer in feet. So I had to change inches to feet. All right, so this is a wheel that's a 1.5 foot radius. That's a pretty big wheel. It's not a cart. That's much bigger than a car wheel. It's like a tractor wheel or something. It's like 3 feet across, so it's big. So it's 1.5 feet. So somehow I want to get rid of revolutions. So where is revolutions going to go? It's going to go on the bottom. And what's the length unit I'm working with?
360.
Well, not the number, just the unit of length in this problem. Feet, yeah. Now, this conversion is going to be special. The reason it's special is because it changes in every problem. It's not like 60 seconds in a minute. That's always the same. 60 minutes in an hour. Never changes. 24 hours in a day. Never changes. How many feet in a revolution changes? Depends on how big of a revolution you're making. Is it a small one? Is it a big one? Well, if we're thinking of a revolution and think of a circle, what's another name for a revolution? Like one full rotation of a circle. It's the what of the circle? It's the circumference. So what we really have to do is figure out how big one revolution of a circle is. Okay? Our specific circle. What's the formula for circumference?
2 r.
2 pi r. What's my radius in feet for my circle?
1.5.
It's 1.5. Be careful if they give you the diameter. Remember, if they give you diameter, you take half of it to get the radius. But they gave me the radius. 2 pi times 1.5. What's 2 times 1.5? 3. So in order to go all the way around this circle, in order to make one revolution around the edge, it is 3 pi feet. Now I know how many feet in one revolution, which is also called a circumference. Now, so that conversion that I put the asterisks above, that's the conversion that gets you from a spinning speed or an angular to linear. That's how you make the jump. Always use the circumference formula. Okay, so let's see what we have. So 1,850 times 3 times pi. And then I'm going to divide that by 60, and I remember that answer from before, so I did type it in right. It's 290.6. That's what anyone else got it? Yeah, so that's 290.6. Let's look at our units. Feet is in the top, seconds is in the bottom. So that's pretty fast. Right? If you think back, we had another problem with feet per second. Where was it? 50 feet per second is about 34 miles an hour. Well, this is almost 300 feet per second. So it's 6 times faster than another problem. So it's like 34 times, whatever it was, 34 miles an hour roughly. So it's like 34 times 6. So it's over 200 miles an hour, which would be, that's pretty fast for a wheel that big. If it's not balanced perfectly, it's going to vibrate quite a bit.
204.
204? Roughly. Okay, so any questions on that? So that's converting linear speed to angular. So tomorrow we'll take a look at 6.2, which is mostly just examples. There's not much notes. So page 324, that's the homework from what we did today. Page 335, that will be the homework tomorrow. So if you want to write both down, you can.
Why does the bottom one look so confusing?
It's just because I had to customize the directions because they don't have them in the book. So I'll talk about that. Okay, so homework tonight, page 324, 56 to 59, 70, and 71. So it's only like, it's not that many questions.